Ladies and gentlemen, this class recording has started. So, yesterday we continued our discussion of accelerated motion, and we talked about the idea that if we have an acceleration, what has to be happening? What is our definition of acceleration? Rate of change of velocity. So if acceleration is occurring, what's happening, Nor? The velocity is changing, and I'm glad you said it that way. That's going to be important a little bit later on. Okay. So yesterday we started looking at this ramp, right? Or we started it on Friday actually, but whatever. And we said the acceleration of the object on this ramp is 2 meters per second squared, and we said that that can be expanded out to look like this, right? 2 meters per second, and that means that what's going to happen? If the acceleration is 2 meters per second squared, what are we physically going to see? It's going to speed up 2 meters per second for every second, and that's why these numbers go up nice and even, 2, 4, 6, 8, 10, right? But if it's speeding up, that means that it's going to go farther every second. And so we spent a lot of time talking about these two relationships right here, right? The fact that we can calculate the average velocity of something in two different ways, and we made use of that to figure out how far something has gone, right? If we know the velocities. Good there? And then yesterday, we introduced the idea of free fall. And we said nothing changes as far as the procedure that we use when we're talking about free fall. The only thing that's different is the acceleration value. Here on Earth, gravity causes an acceleration of 9.81 meters per second squared, which means the velocity changes by 9.81 meters per second for every second that goes by. Good there? And then we applied it to this object that's falling down off of this cliff, right? 1 second, 2 seconds, 3 seconds, 4 seconds. We watch the velocity increase nice and evenly to 10 to 20 to 30 to 40, right? And then we do the exact same thing with the average velocity, right? And we figure out how far it went. Okay? Good there. Okay. So, here's what I want you to do to start today. Here's a picture of a guy. Could be a girl, I suppose. I don't really know. It's not really specific. Okay? This is the picture that you guys don't have in your packet, right? So if you want to draw a little picture of a guy standing on the edge of the cliff, you may do so. Okay? And the thing that's going to change about this cliff is that this cliff is no longer located on Earth. This cliff is on Mars. Okay? He's in a suit. It's Matt Damon. So can't you tell from the picture that it's Matt Damon? So you know. All right. On Mars, the gravitational acceleration is 3.711 meters per second squared. Okay? So, what I would like you to figure out for me is if this astronaut, Matt Damon, were to drop this rock off of this cliff on Mars, how far would it fall in 3 seconds? How far would it fall in 3 seconds? Okay? You know what, Jafar? For the sake of time, because I want to get through this, okay? Let's make that assumption, okay? So Jafar asked, I granted his wish, right? To make this go a little faster, let's round up the acceleration on Mars to about 4. Okay? 3 seconds. Okay? So, and then this here is 3 seconds after it was dropped. How far does it go in 3 seconds? Work with the person next to you. Go for it. There we go. No, it's 18. Devlin, go ahead, I'm listening. Okay, I'll put it up on the board here in a second.
Why did you write both of them?
Isn't it 18?
Each time it goes up by how much? 4. That's how fast it's going after 3 seconds, but how far did it go in 3 seconds?
Oh, yeah.
Is that right?
Wait, that's what I would have gotten.
Okay, so it's 0 minus 3.
Alright, so if you use, like, if you round up to 4, would you have gotten, like, 5.5665 meters?
6?
Oh, I got 6.
18, isn't it? Mr. Plansuck, is the answer 18? Okay. Just wanted to know if I'm right or wrong.
Now, Douglas, that's the average velocity, but it's not how far.
I got 4. Oh, 4.
So wait. Why are we figuring out the average velocity?
Not 18.
Thanks, Captain.
It is 18, Jules. You got it right.
6 times 16. I asked what you got.
I'm dumb. I don't even think
All right, let's go through the process, right? So first, everyone see where the blue numbers came from. Good. The velocity increases by 4 for every second. So it starts off at 0 right when he lets it go. First second it goes from 0 to 4. Second second it goes from 4 to 8. Third second it goes from 8 to 12. So after 3 seconds, it is traveling 12 meters per second. What is 12 meters per second called now?
instantaneous velocity.
The instantaneous velocity, right? But that's not what I asked you for. I asked you for how far did it go. So remember, when we're talking about how far, we have this and this, right? These two equations. And those two equations both equal what?
The average velocity.
They both equal average velocity, right? So, if we look at the interval from top to bottom, what was the initial velocity of that interval? 0. What was the final velocity of that interval? 12. So to calculate the average, 0 plus 12 divided by 2 gives me 6. That's the average velocity.
Now you gotta plug it in.
Then we take this number 6 and we plug it in right here. Right? We're trying to find delta x, because remember, delta x is how far, the displacement. But this interval lasts how much time? 3 seconds. Because I told you how far does it fall in 3 seconds. Right? So now, solving for x here, we just multiply both sides by 3, and that gives us a displacement of 18 meters. Does that make sense? Good? Okay. Before we talk about the next section, we have to talk about a situation. The intent of this exercise here is to try and correlate this, what's going to happen next, with something that's more familiar with you, more familiar to you. Okay? So, open up to page 3 of your packets. Okay? That we've been working on the past couple days. And you should see this picture of Aunt Minnie.
Yep.
First of all, I'd like to say before we start this, everybody needs an Aunt Minnie. Because, as number 1 says, Aunt Minnie gives you $10 per second for 4 seconds.
What?
You need an Aunt Minnie, all right? So how much money do you have after 4 seconds? You have $40. Okay. Yep. I think you can kind of go either way. I think that's kind of the
I
preference
think it's
thing.
officially 1, but like,
I go 1 just because I'm lazy, and that's like, you know, just one line. Feel free to use 2 if you would like. All right. So, relating it back to what we just talked about. We drop a ball here on Earth. It picks up speed at 10 meters per second per second. Why? Because what is that value? That's the what of gravity?
rate.
The acceleration of gravity, or sometimes we call that the free fall acceleration. Okay? So, if a ball is dropped from rest and picks up speed at 10 meters per second, after it falls for 4 seconds, how fast is it going? 40 meters per second. Okay? Okay? Now, Aunt Minnie, right, is married to Uncle Harry. Uncle Harry doesn't want to be outdone, right? So, Uncle Harry also gives you $10 a second, but only for 3 seconds. However, you started with $20, right? So how much money do you have?
$50.
$50. Okay? Now, here's what we're trying to make this connection. You know that if you start with $20, that's not going to change the rate at which you're gaining money, right? Aunt Minnie was giving you $10 a second. Uncle Harry was giving you $10 a second. It didn't matter that you already had some money when Uncle Harry started giving you. You were still gaining $10 every second. Does that make sense? Okay. Now, all the situations we've done so far with our accelerations, we've always started from rest. We started the marble up at the top of the ramp and just let it go. Or we were holding a ball or a rock or whatever and we let it go. So the initial velocity was always what? 0. And then we gained speed from there. Gravity accelerates objects. All objects, regardless of whether they're moving or not. Okay? So, here, if I let this go, and I let it fall for 1 second, here on Earth, how fast will it be going after 1 second? 9.81 meters per second, or around 10, right? Because that's how much gravity changes the velocity. Okay? Now, let's say instead of just dropping it, I threw it downward. When it leaves my hand, now it's already moving. But, and this is the important part, the fact that it's already moving doesn't change the fact that gravity will accelerate it. Okay? And we know that gravity accelerates things at what rate? Let's go 10 just so we're easy, right? Okay, so 10 meters per second. So, in number 4, I take this ball and I throw it downward so that when it leaves my hand, it's already going 20 meters per second. After 3 seconds, how fast is it going to be going? It's going to be going 50 meters per second. Why? How much velocity does it gain every second? 10. But in this case, you're starting at 20. But if you gain 10 from 20, where are you? I hope this isn't a hard question. If you gain 10 from 20, where are you? 30, right? That would be 1 second after you let it go. If you gain 10 from 30, where are you? Again, I hope this isn't a hard question. 40, right? That's 2 seconds. And then if you gain 10 from 40, where do you end up? 50. Gravity causes the velocity to change by 10 meters per second for every second that goes by. It doesn't matter if it's moving or not. The velocity always changes by 10. Okay? Does that make sense? Yes, no, maybe. Okay. Now, for number 5, apparently your mom got wind of the fact that Aunt Minnie and Uncle Harry were just handing out $10 bills at a rate of 1 per second, all right? So, she's making you pay them back, all right? You have $50 and you have to pay Aunt Minnie $10 a second back. When are you going to run out of money? 5 seconds. Okay? Now, question. The rates at which your money is changing is still what in number 5? $10 per second. It just has, well, that's how much our money is changing, right? But in number 1, what was happening to your amount of money? It was increasing. Now it's decreasing, right? Gravity always pulls things which way? Downward. So if they're falling downward, gravity makes them go faster. But if they're going upward, gravity is going to cause them to go slower. How much slower? 9.81 meters per second every second. Hold on to that thought for just a second. Yes. This is now what kind of acceleration? A negative acceleration. Okay? Does that make sense? At least for starters. Okay. Let's go to the back page. And let's take a look at this drawing right here. Okay? This is the one in the top right-hand corner. Okay? And some of the numbers are already filled in for you. Specifically, which column? The velocity. Okay? Now, here's something that you have to keep in mind, because this trips people up on the test. Okay? Time 0 is the moment that it leaves your hand. Okay? So in this picture, this is time 0. Okay? In all the other examples we've done so far, at time 0, what has been the velocity? 0. But in this picture, we're throwing it in the upward direction, so now its velocity is not 0, it's 30. Okay? It's traveling in the upward direction, meaning if it's going up, but gravity's pulling it down, what's going to happen to it? It's going to slow down. This picture is 1 second later. So this is 1 second after you let it go. How much does the gravity here on Earth change the velocity of the object? 10 meters per second for every second. So how fast is it going to be going 1 second later? It's going to be going 20. Okay? This pen is making me angry. Okay? So now we've taken care of this, come on pen, this and this. Okay? Good? This is 2 seconds after we let it go. What happens to the velocity from 1 second to 2 seconds?
Even slower.
It goes even slower. How much slower?
10 meters per second.
So it goes from 20 to 10. Okay? Next picture is how much time?
4 seconds.
Well, it's
Oh, 3 seconds.
3 seconds. What has happened? What happens to the velocity from 2 to 3? It goes down by what? It goes down by 10. And that means up at the top here, how fast is it going to be going?
0.
0. As we've discussed before, what happens to objects at the very, very top of their motion? They stop just for an instant, right? That 0 meters per second is the what? The instantaneous velocity. At the top of its motion, the instantaneous velocity of something is 0. Okay? Does that make sense? Now, it's at rest, 0 velocity up at the top of its motion, but is gravity still acting on it?
Yeah.
Yeah, it is.
Always that.
And so what's going to start happening now?
Falling.
It's going to start going downward, right? 1 second after the top, right? Gravity is going to change its velocity by how much? 10. But now which way is it going? So what's the velocity now? Come on, pen. Negative 10. Why? What does the negative sign tell us? Downward. Right? And that means here to the next one, negative 20. And then here, negative 30.
So 4.
All right? Good there. Okay? Now, let's handle the next column. Except I'm going to do something different with the next column. The next column is labeled as distance, right? I want you guys to do this. I'm going to take this column and I'm going to split it in half. And in this corner I'm going to put distance, and in this side I'm going to put, if my pen will allow me, displacement. Okay? It's a good review, right? Vocab lesson, yes? Okay. So now, let's go here. How far up in the air does that object go in the first second? Come on, pen. I think it's running out of batteries. This is 25 meters. That makes sense where I got that number from.
Average.
The average velocity here is 25. Yes?
Yes.
30 plus 20 divided by 2. How much time goes by? 1 second, 25 meters. So over here, the distance is 25, and the displacement is going to be what?
10.
No, it'll be 20. I don't know.
How far away is it from the starting point?
5.
Except,
Oh yeah, because it goes up.
Wait, is this displacement the one that you have assigned?
right? First one is distance, right? 25. Well, where is it in relation to the starting point?
It's above it.
It's above it, right? So it'll be positive. Okay? All right.
Then that's 15.
From here to here. How far is this, Pat?
I have to go with 15.
That's 15. Does everyone see where that 15 came from?
Why did?
Yes,
10 plus 20 divided by 2.
So the average here is what? 15. And this is 1 second. So 15 meters per second for 1 second, it's 15 meters. This is exactly the same thing we did on the ramp, right? It is. Promise. So that means that the distance now
40.
is going to be 40. Right? And then that means the displacement is?
Yeah, how do you get 40? Oh, it's from the start.
From the start.
And then 5.
Then this is what?
1.
This is 5. Do we see why that's 5? 0 plus 10 divided by 2, 1 second. So that means that the distance traveled is now 45. And the displacement, positive 45. Good 10. Okay? Good there? Alright, here's where things start getting tricky. Okay?
So we just have to subtract.
Okay.
Just use the next one. Or let's leave.
Hey, thought those were double A's, but they're triple A's.
Alright.
Doesn't help me. Alright.
What is that?
The expo marker doesn't really help.
Why? Everything now?
Okay.
So we can save it.
So this is 5 meters. Right? So that means now the distance is 50, but the displacement is now positive 40. Okay?
And then the distance increases 15, so that'd be 65.
So that means now this distance is 65, but the displacement 25. Not yet. And then this distance here, right?
No, 90.
That's 25.
Or well, the whole distance would be.
The total distance would be 90, but joules the displacement is 0. Okay? Now, it keeps going. So here, I'll give you guys this real quick, all right? This that would be that.
As long as we can have it.
Yeah, as long as it's